Yes, Professor. We can able to see.
Okay. Okay. I think thanks for the confirmation and also thanks for the warm introduction. So I hope you are able to hear me, see me, and also see my slides. Okay. So
Yes, sir.
thanks for the confirmation. So I think thanks for organizing such a wonderful workshop where we could interact with the academic fraternity as well as the research community of additive manufacturing. Um, I think we have been in regular touch for quite some time. So I have been visiting St. Joseph's for as a resource person for many of the workshops in the past in the areas of additive manufacturing as well as in smart manufacturing. So it was always a pleasure to be part of some of the outreach activities of this institution. So thanks for inviting me. And also being an online forum and also in a relaxed way, I think many of us can spend more time and can concentrate on the talk. Normally during the days, we get distracted and then maybe this is the after hour of the work and then probably some of you are already home and some of you are already in the office. So it's a good time for us to basically interact. And luckily today in Chennai, we have a very nice climate. So we can spend another 90 minutes trying to basically share whatever work that we have done in our lab, but also in general about what is being commercially available and also what is the current state of the art and what are the future challenges in developing a digital thing for additive manufacturing. Okay. So I assume that the audience already know few aspects of additive manufacturing. I made an assumption that the audience is aware of the 3D printing technologies and especially one of the most commercially successful technology called powder bed fusion. So I have not added any introductory slides or tried to explain that process. So I assumed that most of the audience are well aware of the 3D printing processes and technology. So, and also you have been attending this workshop from the beginning. So I am straight away going into my topic, which is the digital twins for additive manufacturing. So without having any introductory slides on basics of the processes and how it works or what are its process parameters. So trying to basically see that you all have some basics and have read somewhere about 3D printing, or you are a practicing engineer, or you are a researcher currently engaged in research activities in this area. And I know there could be some few undergraduate students who may find it difficult to follow, but I expect them to make it little high level so that they also can understand many aspects of the presentation that we are trying to do today. So before I begin my lecture, I want to give, I want to guide your focus. So today I'm split my lecture into two parts. The first part, I'm trying to explain the building blocks of a digital twin, which we have to do for additive manufacturing. The second part, I'm presenting one of the PhD students' work, Dr. Hamnath. So the first part will be typically focusing on the building blocks and how to build the models for digital twin. And second portion, I'm trying to show how it is to be validated, verified, and then what are the efforts that is needed to get the model. Hope it sounds like a plan, and then I hope I can continue discussing this. Okay, now I think additive manufacturing, I assume that many of us understand as defects as equal to any other conventional manufacturing, right? So even though we have a lot of advantages in terms of time compression, increased complexity, faster turnaround, right? So complete digitalization, customization, hyper customization, and in fact, consolidation of parts and functional integration. So we have all these very interesting capabilities of additive manufacturing, opportunities for additive manufacturing, but still it is a thermal process, especially the powder bed fusion process. It suffers from the defects such as porosity, distortion, warpage, residual stresses, right? So it also suffers from inaccuracy due to stair-step errors and stuff like that. So I can paint a very rosy picture of additive manufacturing, but still getting the first part right in the first attempt itself is a lot of challenge for many industries. So industries wanted, the help of academicians or more generally technology from academics which are commercialized to control or to predict some variability that is there in the additive manufacturing, right? So one of the important impediment for additive manufacturing to be adopted by industry is its cost. Mostly this technology is very expensive. The powders are very expensive. And right now, the cost of the additive manufacturing compared to a conventional manufacturing part for a high volume, a low variety is much, much higher. Whereas for a low volume, low variety, 3D printing stands tall, right? So we all understand that part. But for even making some aerospace parts or medical healthcare, where it has killer applications, right? So where it has a lot of capabilities or opportunities, it still needs to go through a very rigorous qualification procedure. Meaning that the component which we make in additive manufacturing, if it has to fly in an aircraft or in a space application, it has to go through some quality checks. We call normally this as a qualification. So when we do qualification, we have to do a lot of standards-based testing, starting from the feedstock to the final post-processed part to test its property, to its function. So then only that model will be 3D printed model or 3D printed part will be accepted for flight or things. Or even it could be implanted into the human body, or it could be used in automotive. So there are a lot of industry relevant qualification standards and procedures, which are now well established. And also it's currently a lot of benchmark parts to qualify the machines, qualify the feedstock, qualify the technology is also being done. For example, NIST, where I worked earlier, had a NIST benchmark parts. You can make a benchmark part and qualify the process capability of that machine. So what is the minimum wall thicknesses and what kind of errors that we get for different hole sizes, and then will you be able to get cantilevers? What are the overhang surfaces? What could be its surface points that you can achieve? What is the hardness and stuff like that? Apart from that, we have to also do some functional testing for its behavior. So we have to check its properties, sometimes creep, sometimes fatigue, sometimes compressive tensile stresses. Sometimes we need to study its wear behavior, corrosion behavior. So we have to do a lot of functional testing and also qualify these parts for any function that it will be subjected to any loading conditions or corrosive environments, or for any wear or frictional performances. All those things we have to take care. Now, the major challenge here is that when we try to do all these experiments to get it qualified, having a simulation tool or a digital twin of the process helps them to fast track it. Right. So, for example, a turnkey project of converting a conventionally made fuel nozzle into a AM-based fuel nozzle took a lot of time for GE, right? So even companies which are considered to be having nearly infinite resources to at their disposal can still work, can still find it difficult to basically iterate those designs and then qualify those designs and successfully qualify. You might have seen the fuel nozzle of the LEAP engine, which is the GE poster by a successful additive manufacturing. Increasingly, when industries wanted to adapt this AM and kind of leverage the advantage of AM, they needed digital proving technologies called digital twins, right? So what are digital twins? Digital twin, I'll just try to get my pointers, laser pointer. I hope you are able to see my pointer. Yeah. So the digital twin, it involves developing models like mechanistic models, control models, and statistical models, or machine learning models, where you need to generate a lot of data like literature, sense data from the process, simulation data, literature data, and then use machine learning to reason, right, and update these models. And then when we use the real world 3D printed parts, which could be simulated in a virtual world. So this is typically a what is called a digital twin. Digital twin is an exact physics-based representation of the process in the computer that we can use to basically create it. But whether we should use a big data, whether it's use a machine learning, or it should be simply a physics-based model, it should be a statistical model, or it should be analytical model, an empirical model, or a combination of all. It depends upon different types of processes. Why? Because some processes are so simple, some processes are so complex. So if there are complex physics involved, which actually makes it very difficult for the manufacturing process to be simulated, basically go for a combination of, machine learning models, empirical models, analytical models, and stuff like that. So we have to combine all of them. So today the buzzword is the physics-driven artificial intelligence, or what is known as first principle-based models, giving a lot of data, generating data that will be used to basically learn machine learning. So essentially what we are trying to do is to control the amount of experiments. We are trying to reduce the number of experiments, which you need to basically qualify the part. So means like, so let's say, for example, you are searching for some creep data for a different process range. So you can do only an optimized process parameter and test only a few parts rather than testing it for a wide range. Because in the computer, in the digital twin, you can test for a wide range and then freeze to few very optimized process parameter for which you can do experimental testing using standards. So that means we are reducing the number of trials. We are reducing the number of experiments that are needed for qualification through digital twins. So, okay, so we had simulations for quite a while. Why this word digital twin has come? Because the simulation models itself cannot be directly used until otherwise we build a digital twin of it, where you have the CAD models coming in, control sequences coming in, tool path coming in. So since you try to actually mimic the entire machine or a technology, and then input that data into the models, then it becomes a digital twin. So you can have simulation models which are loosely integrated, then it is not called as a digital twin. When you tightly integrate the simulation models with all the other input data, then it becomes a digital twin. So I'll show you what are the digital models for a simple powder bed fusion process involved. So starting from the powder flow, powder dynamics, and then how the laser interacts with the powder, and then the fluid flow or thermofluidics or melt pool, how the melt pool behaves, and how the microstructure evolves, and how does the residual stresses and distortion form. So a complete coupled model of all this physics is what is making this process much complex. So a digital twin model, a digital twins for AM should consider powder dynamics models, heat source interaction models, and also melt fluid thermofluidics and heat transfer models, and microstructure evolution models, and finally trying to distort simulation. So if you want to basically understand distortion, then residual system distortion. In my lecture today, I have focused on studies that we have done on distortion, so I am restricted to distortion, but you can do it for any response. For example, here, what are the different responses you can study is like you can see that you can study defects like porosity, gas-induced porosity. You can study grain growth and microstructure, stress and distortion. You can also derive optimized process parameter for a part for any functional thing. Right. So for that, from the physical part manufacturing, by conducting few experiments, you would do a lot of measurements and generate some data, which is sensory measurements and data, like temperature measurements through temperature sensors and other types of sensors. And you also have simulation results. You have micro scale models, which are like melt pool models, mesoscale model, which is layer-wise models, and part scale model, which is very porosity-wise model. So you need a multi-scale physics-based simulation models, and also data from the physical part manufacturing. This is the physics. These are all based on first principles of physics, and this is based on the real-world data collected from the experiments, which actually goes into building the physics-based simulation models. And several inputs are required. For example, your model geometry and the toolpath scans like raster, circular, contour parallel, zigzag, whatever it is like, and then fractals and stuff like that. And what are the input powder material, feed powder properties, and then the laser kinematics, like for example, velocity, power, and then what is the hatch spacing and things like that. So, and then monitoring and measurements, like what are the measurements that you do, like environmental control, temperature, pressure of the chamber, and then part bed temperature, and also the other measurements that you do on the chamber, like whatever measurements that you do from the chamber. These are all the record inputs, and you get the outputs. This is typically what in a normal simulation does. In case of a digital twin, what happens is like you get the same thing. You have the CAD, you have the STL, you have the toolpath, you have the manufacturing process simulation, but you also create a digital twin of it, what is known as a digital system. Here you give the geometric parameter, the material property, and process control parameters. Then you build a high fidelity model, so which is typically a physics-based model. From that, you run down to a surrogate model, which is typically a more faster prediction of models, where you have several objective functions, constraints, and reference trajectory from the domain knowledge, which is given. Now you can use a model predictive control from the surrogate model, where you can convert from digital to physical feedback. So you can see that you have the physical to digital, where you have the measured variables from the physics or from the experiments, and then the predicted variables. They can update the surrogate model parameters in real time. And then you can use MPC or model predictive control to control the manufacturing process in real time. So you can see this is a full feedback system using digital twin. Okay. Now in this lecture, I am trying to focus on three important aspects. The first one is how to build such a high fidelity model. And then from that physics-based high fidelity models, how to basically create surrogate models. And then what are the surrogate models that needs to be built for a powder bed fusion process, and how we can use model predictive control on them. This is how we are going to basically focus on thing. So first of all, let us just understand what is a surrogate model. So what happens is, if you really look at two, as I said, empirical, statistical, derived, experimental black box models are there. And there are white box models because we understand the physics, what's happening, the data. So this is a physics derived relationship, and you have statistics derived relationship. Both of them enter into a black box, and white box enter into a gray box, which is data sets which understands the behavior of the system. And some data also come from the literature. And then we use machine learning models, which is readily interrogatable. Either you can use supervised and unsupervised learning, especially if you want to do a classification and regression, clustering and anomaly detection through unsupervised learning. And also you can actually use a reinforcement learning to improve the model accuracy and things like that. So you can see that it can be improved. So which is coupled with the sensor data from a physical twin. So in a real time, you also have a digital twin to physical twin. So real time data goes into the digital twin. And also the digital twin uses model predictive control to control the physical twin. So you can see that this is how the surrogate models, which is going to work. So we call this as, the process intelligence model, which is typically the models which increases physical insights to some level. And this is the surrogate machine learning model. And then the process under supervision. So this is the complete surrogate model. Now, what are the building blocks? So this is the overall picture. But when it comes to specific to powder bed fusion process, what are the different models that we need to build? And what are those connections between them? Right. So for example, some of the basic building blocks of a surrogate model is a multi-scale model and a multi-physics model. Right. For example, so we need to understand the powder dynamics model, as I said, the powder spreading model, which will determine the surface shape, which will be controlled by MPC through the surface shape. And we need a melt pool model, which is in the, you can see this is also in the micro scale, this is also in the micro scale. We get the surface morphology, packing density from here. And then we have a thermal history from the melt pool model, which is taken to the microstructure model. And the microstructure model can be used to predict like thermocalc and other thermophysical properties from the microstructure model. And then you also use the same thermal history to predict the residual stress and distortion. And also thermomechanical properties comes from the microstructure model because the evolution of the properties is controlled by the evolution of the microstructure. This is typically in the mesoscale in centimeters, the residual stresses happens. And structure property relations like cracking, porosity, and all those things can be lack of fusion, can be also determined from the melt pool model. Like you can get the porosity values, lack of fusion from heat. And that could be used to basically understand the complete linkage of structure, the process structure, property, function, behavior, mapping. So that could become a full-scale model. So this is what we call as multi-scale and multi-physics model. Now, when I say multi-physics, we need to really go deeper into the process to see what are the multi-physics involved in a typical PBF process. Okay, so these are the physics. For example, if you look very closely into the powder bed fusion process, so you will see, this is the surface finish of a layer. You can see laser beam coming in here and then melting the powder pool. This is the powder particle, and this is the previously melted layer. And then the particle engravement due to gas expansion, though, and you can get a plasma flume. This is the direction which the laser is scanning. This is the powder, and this is the complete melt zone. You can see there's a lack of fusion, crack, and porosity. And this is the melt pool, which is having a Marangoni flow. So Marangoni convective flow because it draws the powder inside and moves inside due to the Marangoni convection. Here also the movement is like this. So you can see the powders are drawn into the melt pool. And you have some vapors being produced, some spattering also occurs with the melt jets moving here and there. So you can see it's a complex thermal fluid dynamics happening here at the exact intersection. And then you have a solid state solidification and transmission happening here, which is the intrinsic heat treatment in the heat affected zone. And then after that solidification, you can see some microstructures formations and then defect formation here. And then here is where the solidification kinetics can be very used. And you can see gas pores, gas gets entrapped, gas induced porosity. And this is the process induced porosity because of the lack of fusion. So you can see all kinds of defects, all kinds of physics. So you have particle dynamics here for the gas model, because the particles are going to come and form a layer. This is the particle dynamics model. Here is the thermal heat transfer plus fluid dynamics model. And here is a solid state transmission model, especially for the solidification model, solidification kinetics. And then the solid mechanics model is for phase deformation. So this is the real solid mechanics model where a distortion happens, residual stresses get relieved and things like that. You can see this is the complex physics. This is the multi-physics that is getting involved. And also the scale is also multi-scale, because some phenomena happens at the micro scale, as we have seen in the previous slide, that some happens in micrometer level, some happens in the macro meso scale, some happens in the large part level scale, right? So then it becomes, the model becomes a full multi-scale model. And here is where the simulation interest happens. For example, when we are trying to basically use a computer model, typically, which is to do the simulation, the reality of the interest, we get you normally get from the reality of interest, you create a mathematical model, and then we implement it as a software. For example, software like general purpose multiphysics softwares like ANSYS, Abacus, and some other commercial tools, which I could not say. And there are specific purpose softwares like Cinefact Additive 3D and stuff like that. So Pondu, Pravaha, and all those kinds of software. So you have to basically do the validation, confirmation, verification. So once you build the model, it has to be verified with the mathematical model again. So when you build again, the mathematical has to be conformed with the reality of interest. So you can see it's a reverse cycle. And this is where the modeling input data goes in, and then you get it. And this is where you have to verify and model. In today's lecture, I'm going to show you what we have done, how we built the mathematical model, how we built the computer model, how we verified it with the confirmation experiments. At each stage, at each step, how do we verify our models, how we built the circuit models that I'm going to show you. Okay, the first to start with the thermomechanical simulation. So this is the first physics-based simulation that we do. So there are many different types of thermomechanical simulation, because when the laser comes in, it heats the powder bed, and it is a thermal process. The heating happens through conduction and convection as well as radiation. So they are forms as the boundary condition. Normally, this is normally solved as a moving heat source problem. So we have a moving heat source. The heat source is moving. So you can solve a moving heat source problem in many different ways. The simplest way is you can solve it as a Stefan's problem, or you can solve it as a coupled thermomechanical problem, or you can solve it as an uncoupled thermomechanical problem. In coupled thermomechanical problem, you're going to basically change every element after taking the results from the previous simulation. In uncoupled, you first solve the thermal and then bring it to the mechanical simulation, and then update your next iteration for the thermal simulation, right? So here we have the initial and boundary conditions. The initial conditions are the initial temperature of the powder. The boundary conditions are typically the, what is happening in the convection is happening in the surroundings and things like that. So then we have to model the heat source. Normally, lasers and electron beams are used in powder bed fusion. So lasers are typically modeled as a Gaussian beam, having full width of maximum, typically used with, which has a maximum peak intensity at 1 by V or 1 by U square from the tip of the maximum intensity. And many times they use element birth and death, which is a very old concept, which has been used in many different approaches. Or sometimes one of the biggest drawbacks is you get an approximate result, because all these are numerical methods. And sometimes you can use a dynamic mesh where you can change the size of the mesh, where the interaction between the laser and the material is happening. And other regions where not much interaction between the heat source and the material is happening, where you can use a coarse mesh and a fine mesh. That is what we call a static mesh. Static mesh means uniform meshes all through, whether it is fine or coarse. But in dynamic, you change from coarse to fine as the laser moves in. So that's called a dynamic mesh. And mostly this comes at a very high computational cost and time, because they are very time consuming, because you have to do it for each layer. For example, if you take a very large part, so when you drill down into the individual tool parts, these tool path segments are, even though they are very, very small or even longer tool path, for each tool path, it takes a lot of time. So to simulate for an entire part, it will be extremely computationally expensive and computationally intensive to do that. So that's one thing. So normally what happens is like you input the solid model element type for the thermal analysis, you input the density, physical property, thermal properties. Here you input the physical properties, input the mesh size, conditions, boundary conditions, process parameters. Here displacement force, here the boundary conditions are convection, and heat source model is used here to basically do the thermal instructions. So this is how it is done. So normally you take a material model, part model, process parameters, boundary conditions, heat source model, and a scheme, whether dynamic or static machine scheme. You do the pre-processing. For each layer, you go to the, you iterate for each layer, layer 1 to layer 10, depending upon the number of layers in the part. For each layer, you iterate to each scanning track, do the thermal analysis, get the temperature field, apply the mechanical boundary condition, do the mechanical analysis. And when that laser scanning track is done, you go back to the next track and then try to basically do it. So you iterate it until all the tracks for a particular layer is done, and also then iterate it for all the layers. Then calculate the residual stress strains and displacement fields at the mesoscale after you have the temperature field which is there, which you have collected over thermal history is collected over P of, let's say for example, T of x comma y comma t is the temperature that you got over time. Then you use that to basically calculate the residual strain and displacement field using that coupled thermomechanical analysis and do the post-processing to visualize the results. So similarly, you have to also do the fluid flow modeling where you can use either use the Eulerian domain or Lagrangian domain. So in Eulerian, you can use volume of fluid technique. Here you can use SPH or PBD, which is the smooth particle hydrodynamics model, or position-based PBD. So all these approaches can be used. So I have not given the governing equations for thermomechanical because assuming that many of you are familiar. Very similarly, here you use the conservation of mass, conservation of energy, and conservation of equivalent energy. And also we need to identify the liquidus and solidus zones for the conservation of energy. We use specific heat as a function of latent heat of fusion. So we can see that for the liquid region, we are defining the temperature is above the liquidus temperature. This is the liquid region. A temperature between the solidus and liquid region is a meshy region, and then below the liquid is solid region. So we define the fraction, liquid fraction, and use the liquid fraction for the latent fusion. So for example, most of our mechanical properties, especially powder properties that we use, sometimes we use a bulk property, sometimes we use a, they may not be accurate. Then we use typically a homogenized material properties for 3D printing, or sometimes we use the bulk density, or sometimes we use the bulk property, sometimes we use the powder properties. But here we also have to use properties which are variation with respect to temperature. So we need to basically take material property as a function of temperature, then it becomes an implicit modeling scheme. And we solve the conservation of momentum equation. In addition to that, we also give the volume fraction for density. Here you can see the density, specific heat capacity, and also the fluid fraction, the liquid fraction. All of them are being calculated based on the mass fraction of the liquid. From that mass fraction of the solid, right? So volume fraction of the liquid. So then we can use these input properties in the simulation to simulate the fluid flow. And many times, as I said, in thermal also we make a lot of assumptions, thermomechanical. Here also we assume it is a Newtonian fluid and incompressible, follows a laminar. And then we also give additional boundary condition for Marangoni effect, which is basically going to make the fluid flow into the Melton zone. So these are the conditions. You can see some of the outputs, simulation outputs of the fluid flow, which gives us the temperature over time, or the velocity over time. So this is the temperature over time for a nickel alloy for a 200 watts laser at 1 meter per second scan speed. This is the temperature distribution on the surface, and you can very clearly see when the molten region, liquid region, mushy zones, and the remaining powder zones which is unmelted. And then you can also see the surface characteristics of the molten zone. So you can see the different temperature regimes, which is corroborated into the real world laser parts. So this is the melt pool dynamics shown along with the velocity field. You can see in the XZ plane. This is the temperature distribution on the molten fluid, the red melting material here. You can see showing a laser beam how different particles get melted, and then the melt zones and the temperature distributions and the velocity profile of the melt zones are also shown. The velocity field is also shown. See, okay, so now I want to give you a very different perspective. When you want to do such a fluid flow and the thermomechanical simulations for a large scale, um, um, part, it is going to consume a lot of time. So there has been a lot of effort in the past to reduce the time to do the faster prediction. So you can see that this is one of the expected calculation time in terms of number of elements. If you have a number of elements which is around 60,000, so you can see that it goes up to 6 days, for a layer of 120. So it means like for a 20 layer part, you can see it goes up to even 4 days to get the result. So you can see for each individual layers. So for a one single layer or two single layer or number of layers, you can see this particular kind of a behavior. So you have to wait for days to get, a simple 120 layer. So imagine an industry trying to basically simulate and predict its behavior, and it has to wait for 6 days to get simply a 20 layer or a 120 layer simulation is completely unacceptable. So we need to basically fast track. So there are some time reduction approaches. So for example, here, this is one of the baby steps that people have taken to reduce the time by using typically coarse and fine mesh combination, which is called dynamic mesh or dynamic adaptive mesh refinement. So you're refining the mesh in the zone of influence, and then trying to basically, you can see the mesh size is very, very fine here, and it is little coarser and then much coarser at zones which are where the laser is not there. So like that, you can do the time reduction by reducing the computational load, by increasing the by reducing the number of elements by using dynamic adaptive mesh refinement. Right, so you can see that when you use a dynamic without a uniform, the running time for a simple file, also its file size is shown here. You can see if you use a dynamic, if the file sizes become down from 7.9 GB to 3.75 MB. So it has reduced to 3.75 MB from 7.9 GB. The file size got reduced. And also you can see the total time, running time of the simulation came down, I think almost 5 times, right? So 35 to 7. So like 3 times. Like you can see the running time and comparison between the dynamic and uniform. This is one way to basically reduce the time. So when you use let's say a stepwise mesh portioning, like for example, each layer you want to basically at each step you want to do the step meshes to be portioned. So you are trying to basically increase the mesh size after each step. So you can actually reduce the time. You can see that so initially this is the one approach where you have used uniform meshes for different degrees of freedoms. So for 300 layers, you could see that the degrees of freedom was somewhere around 1.5 into 10 power 6. But here you can see if you use a coarse-wise coarsening mesh scheme. So only this is the fine mesh and this is the rest of the coarse mesh. You can see it is reduced to very small amount of time. So you can see that the time reduction approaches are very, very favorable. And many people try to also not do the scanning for individual track path, but they wanted to assume each layer as a one go. It is manufactured as a one go. So this is typically what we call as a layer by layer heating. So instead of simulating the laser movement as a moving heat source problem, so people have solved this problem by typically assuming each layer to be heated and then formed. So they did a course. They had a very approximated simulation wherein the entire layer can be simulated at one go. So what they did for a one melt pool simulation, they allowed it to basically reach an equilibrium condition after a certain time. They used this as they built a constitutive model from it, and then they used the constitutive model to simulate for each layer. So this is how it is done. And there are many commercial software. Still, you can use it. For example, Autodesk, Netfab, ANSYS 3D Sim, Additive Labs. Not exhaustively, I'm listing all the tools, but I'm not endorsing all the softwares. They are fit for the purpose. Just for people trying to basically get them, first wet their hands with the simulations. You can use these commercial tools. The licenses are available. You can try them. But I'm not endorsing this software. But what I'm trying to say here is you can just commercially build your first simulation models using them. So this is most of them have come from academic world. For example, this one came from Professor Brent Sticker, who is the author of the famous additive manufacturing textbook. So he worked at ANSYS for quite some time. Now he's I think happily retired from ANSYS. So he has we formed a company called 3D Siemens, which got integrated with ANSYS, and it uses a very interesting modeling phenomena, thermomechanical phenomena, to basically do it. And you can see his papers, how the methodology was developed and how it was integrated into ANSYS 3D simulations. And Autodesk NetFab came from another university. Additive Labs come from another university. Like many universities have developed the simulations, and then they've been commercialized by software majors across them. So another important idea that came into macro scale simulations is the inherent strain method. Like, for example, if you want to do the distortion prediction, as I said, you have to do the thermomechanical simulation and take it to a part scale and then do the residual stress distortion calculations on the part scale from the temperature field and obtained from the single track simulation. But instead, there have been some interesting approaches. The Niels Keller and others have adopted the inherent strain method. They are already aware. It's not like the inherent strain method is very recently developed. These methods existed for the welding process for last 30 years. People in the welding have been using these methods. So in an inherent strain method, what you do, you actually take an STL file, which is like a cantilever specimen like this, which has got these cantilevers. So you input the heating, process parameters, hatching patterns, and material properties, and then you estimate the local inherent strains from the experiments, calculate them, because you are going to basically cut this one off from the build plate. So then it is going to basically deform like this. You can see the deformation happened because of the relief, visual is relieved. So you measure those strains, and then you solve the inverse problem to get the inherent strain. So from the measured strain value. So for that, Niels Keller has developed very interesting methodology. In fact, his software is also commercialized. So here you can actually do a micro scale heat source model and a mesoscale hatching model. Then you can take those inherent strains measured from the cubic heat sources and put those inherent strain here. So you have a bulk material for the individual layer. You can actually do the inherent strain in the macro scale layer model. So this is done using simple experiments. So you can see that you have a different kinds of hatching strategies you do, and then different levels of deformations you can get. So you can see that the scanning pattern has a larger influence on the strains that you can measure. And using the simulation also, you verify the measured values of the deviations and verify that with the simulations from the experimental, and then you can just use that to calibrate in the software. So the calibration happens like this. So you print the cantilever specimens along multiple directions, like parallel to X, parallel to Y, 45 degrees, and also 135 degrees and things like that. You can print all the cantilever specimens. You can change the scan speed, layer thickness, laser power, scan strategy. And then once you remove the supports from the cantilever using wire cathedium and you remove it from the build platform, it will deflect, measure those deflections along the top surface, along the center line of our cantilever using equidistant points for each of these cantilevers, and then input that into a calibration software. So for example, this is the measured inherent strain. So these are the different samples that you have tested: 0-degree sample, 45-degree sample, 90-degree sample. You input those deviations, whatever you have measured over time, and then you can calculate the inherent strains, which will be used to basically try and calibrate that inherent strain for different calibration steps, like 25, 35 calibrations you can do for different orientations. You can find the maximum target and the maximum deviations from the simulations, and then you can define the layer thicknesses, and then you get a constitutive model. And this model can be used to basically simulate. Okay, so let me just show you one of the inherent strain method. I think I have a huge bunch of slides explaining the inherent strain method. For the want of time, I'll point you to some commercial softwares which uses the inherent strain method. For example, Simifact Additive, which also uses inherent strain method based models to simulate. Amphion from Additive Works, which is the Niels Keller, and GeoNex from Udipal. So you can see some of those tools which actually use inherent strain method. So these are very faster, right? And another important thing is, like, we are doing all this for calculating the thermal history and then the fluid flow dynamics, and then we have done part level simulation in inherent strain. But next is we need to also look at the structural models, like microstructure evolution models. So how do I then correlate the process structure property? How do we model them? So for that, I think you need to basically work in different length scales. For example, microstructure representation. And there are sufficient amount of publicly available coding schemes available for example, you can use cellular automata, or you can use some stochastic modeling techniques like Monte Carlo techniques, or you can use physics-based models like phase field to generate microstructures for additive manufacturing. In fact, San Diego National Laboratories, for all your knowledge, you can use the simulation tool that is already available. So you can use the general already existing open source codes to generate microstructure from AM. And that could be used to basically, those comes from the process modeling. So first you have to do the thermomechanical modeling, understand the grain structure evolution and microstructure modeling, and then we get the grain structure. From that, we do the property modeling, and then do the von Mises and other kinds of structural things. You can see that this is the part scale, and this is the micro scale, and this is the meso scale, and this is the, you can see different length scales. We are working on a multi-scale model, how they actually go into looping here. So here you can understand the solidification response during solidification, how microstructure happens. Here we can do the thermomechanical response. And here you can see the physical solid mechanics, and then responses to basically physical properties based on the structure. Right. So this is the coupled model where you have a temperature field plus the phase information coupled together. For example, this is the Mel-Pool dynamics model where you are trying to model the couple. So you get the temperature field, right? And then you get a microscopic simulation model. Here you're trying to basically simulate the grain growth, and then use that phase information again here to create that solidus liquidus information here. So you can use as a coupled method. So here you can use both the phase information and the temperature information. That's why you can see some of these arrows are bidirectional, meaning when you're simulating, the information is being passed on back and forth, right? So that is how the temperature and phase information is being used in the coupled model. Right. So what is so involved? Like what is to be so involved in this? So if you see, for example, the energy heat source input models are needed. Computational process modeling for microstructures, nucleation evolution is needed, and micro heat source modeling is needed. Macro heat source modeling and microstructure evolutions are needed. And then we have to understand experimentally how this microstructures influences the property. Right. So we need to basically see a lot of informatics driven uncertainty quantification based methodologies. Like, for example, we can do image based data collection, use reduced order microstructure modeling, image based mechanistic plasticity, multi-scale fatigue modeling. On all those things, you can use it to basically fine tune this. That's why it's very involved. So, for example, when you try to develop a full linkage between the process structure process, it actually involves a lot of uncertainty quantification, understanding the data validity, understanding the reliability of the data, and also verification and validation of the data that we have built, and understanding the feasibility of those different types of alloy. For example, for a simple alloy that are currently used in 3D printing, like SS3167, it's quite easier. But when you have eutectic alloys, or you use ternary, not binary, but ternary alloys, for example, even for AL10 and MGSI, so where we have aluminum, magnesium, and silicon. So understanding the phase differences, what is happening in the ternary systems is more important. Like for aluminum alloy, and even for eutectic alloys, it becomes a little more complex to simulate the phase properties, phase to structure and structure to phase, and then to thermomechanical. It's become much complex because you have distinct melting temperatures for different materials, and they form distinct boundaries, whether there would be diffusion, whether there would be dilution between the different materials, how the alloy formation will happen, what are the different types of structures that you get out of that at different temperature zones. It becomes much complex to basically do such a simulation for modern materials that are currently being explored, like eutectic alloys and things. So it's a very involved process. So that's why for another 10-20 years, I think in the people in the AM domain can take up some problems, and then they can solve it for 10-15 years, and then they could publish some 100 papers in this. So there's a lot of scope in terms of how you can actually bring value to all these simulation methods and linking them together. And when you do the integrated approach, like for example, when you are integrating the computational tool set approach, right? So we need to understand the process structure. For example, first one is calibration of the thermal response. Second is the microstructure evolution analysis, and then the experimental study of the process parameters. And we have to then create a macro scale thermal modeling. From that, we have to predict the properties like ductility, residual stresses, UTS, and elastic property. And also from the non-equilibrium solutions, local non-equilibrium solutions, you have to also understand porosity, anisotropy, and surface roughnesses and all. So you can see that it is a very involving, much complex teamwork that needs to be built to basically do it. So when you couple experimental work, so for example, when you have a microstructure formulation from process parameters, this is an example from DED, direct energy deposition, you can understand how the fine coupled experimental and computational framework can be used in concurrent multi-scale coupling. That means you are taking results from the macro scale and then using that results in the micro scale, and then again taking the data to the meso scale to basically again influence it in the macro scale. So this is the coupled multi-scale where you pass down the thermal history to each fine scale over time, and you upscale the microstructure property to core scale. Like for example, from the micro scale, the properties are upscaled to the larger dimension or higher dimension of the coarser scales, but the thermal history is passed on to the micro scale and the fine scale. So you can see that this is how the coupled experimental and computational framework can be used. And there is the linkage is always very difficult to get. For example, you have different process groups like DED, lasers, electron beam, different materials, right? So different thermal inputs and different kinds of process parameters, which results in different range structures. And you have to test them using, coupon testing, destructive testing to understand its mechanical behavior. So the design loop involves, finding the optimal process parameters and linking them into process performance into property. So complete link between process structure property needs to be established. So a lot of experiments also are needed while you get these results. For example, sometimes you may not get the result that you want. Your residual stress predictions may not be proper. So you need to use a lot of characterization techniques. For example, we need to use a lot of microstructure characterization and mechanical characterization for strength, toughness, creep, fatigue. For microstructure, we have to use SEM, EDOX, EBSD, TEM, AFM, and XRD and all. XRD is a very low-cost technique for measuring residual stresses on the surface. If you want to measure subsurface residual stresses, you can go for an expensive methods like neutron diffraction and other methods where you could measure the subsurface residual stresses. So you have to employ these characterization methods to validate your scale-to-scale transformation of the property to function. And also you have to use mechanical characterization to basically qualify the process to structure relationships, right? So these are all to be used. So this is from the process structure, we have to use this set of characterizations. And then when in properties to performance, we have to use this set of mechanical characterization tests. So this is how, someone doing a research to build a digital twin has to focus. Okay. So next I'm going to show you some basic work that we have done in the building blocks leading to multiple physics. I'll show you some work that we have done in our lab. So here, these slides are from one of my doctoral student, Dr. Hemnath, who has graduated, I think, a couple of years ago. So his approach that he has done is he did a Fahrenheit simulation. He used a Fahrenheit method for temperature simulation, and he simulated thermal data sets for various process parameters, and he used machine learning algorithm like GPR, Gaussian process aggregation, to build or predict the thermal history. And then he used mean absolute prediction error to check the validity. And also he simultaneously did the fabrication using PDF. He input his thermal data obtained from the experiments to fine-tune those results and also validate those results. So this is how he has done. The overall methodology is like this. So you build a surrogate model at different scales. For example, we built not just a surrogate model in one scale, but this is for the micro scale, this is for the meso scale, and this is for the part scale we have done. For example, in the this scale, we built a temperature model, temperature prediction model here from the surrogate model from here. And we also built a distortion prediction model here. And then we used shape descriptors assessment for shape description. So you can see that. So we used temperature prediction models where we did a FEM simulation here. And then we simulated thermal data for various data sets. We trained and predict thermal history. So this is the first part. And the second part, we did this for to prove that it works in the mesoscale. We took some complex structures which are very unique for 3D printing. Like one of the things that we have selected is a stud-based lattice. You can even choose surface-based lattices, but we use stud-based lattices to prove that a distortion prediction technique can predict faster with respect to those kinds of very intricate geometry. So that's the methodology that we have adopted. We have used, we have designed the unit cell for the lattice structure, simulated the residual stress and distortion. We generated the data sets, and then we trained using artificial neural network model, which is our surrogate model for the macro scale. And then we very uniquely define something known as a shape descriptors, which can even fast track the simulation by evaluating some shape descriptors from the 2D shape descriptors from the 3D part. And then use that as a means. If you understand the correlation between the shape factors and the distortion behavior in the macro scale, so we could very quickly simulate it in a faster way. So those are the things that we have done. I think I request the host to basically control. There are people who actually could write onto the slides. I expect the host to.
Okay, Professor. Okay, I'll do first. I'll take care of it.
Okay, thank you. Okay, so this is one question. So I have a few questions in the chat window. I'll come back to it towards the end of it. So I'll show you the thermal simulation first. So thermal simulation, first we started with the thermal modeling. We started with a simple this is the energy balance equation for a three-dimensional heat conduction problem. And this is the initial condition, initial temperature, and then the heat source is modeled as a moving area heat source. And then we defined other boundary conditions like convection and radiation, right? So this is the normal how we built a FEM model. So then we defined the Gaussian distribution function for the heat source is modeled as a Gaussian heat source, and we trickily used velocity here. For example, since it is moving along x, so we used velocity along the x direction. So as we increase the velocity, that we actually move the laser over along the x, so x gets varied when the velocity, speed, and time gets varied. So for each time step, we are able to move the laser over the path. And we also calculated the absorptivity based on a particle dynamics model. The absorptivity is typically influence the total energy input. So from the particle dynamics model, we calculated the absorptivity, and that is effectively used here as the absorptivity of the powder. And then we have used this expression like laser power, and Q prime is typically the distribution of the heat flux, which is to be input in ANSYS. So we made certain assumptions here. So we use laser beam as a heat flux, have a Gaussian distribution, and material we have considered isotropic, but for simplicity. And absorptivity is considered to be same as that of the solid material. So here we have, as I said, the absorptivity of the powder, we calculate from the particle dynamics, and then we created an equivalent absorptivity, which is corresponding to the same solid material. We also did a conductivity of the porous powders modeled as effective thermal conductivity, taking into the powder particles. So because we did a conductivity of the air plus conductivity, then we know the volume fraction of that packing factor of that powder bed, and then we used the effective thermal conductivity as a material property. And then we have used a substrate, SS3161 substrate, which is considered temperature-dependent material properties are being used there. So what we did is, like, as I suggested, we have the input process parameters as different feature vectors, and we did allow multiple simulations, and we understood the input of the dependent variable to the independent variable, like the temperature to its different process parameter inputs, and then we trained the surrogate model. And then we are able to get an output. For example, this is a very expensive way to do simulations. Since we did the very cheap training and employing a surrogate model, which is relatively inexpensive, so we are able to basically improve the efficiency of the analysis. So the GPR model, one of the very important thing is how to basically do the hyperparameter tuning. So we use the Maton 5x2 kernel function. After we tested with so many different functions, we found the Maton 5x2 kernel function to be more effectively used in the case of temperature prediction, right? So we have seen that this function is during our hyperparameter tuning, we are able to do. This is the covariance function that we have used in the Gaussian process model. So this is the covariance function. So, and we also did a physical, and these are the input physical properties that we have used for the simulation. And this is the elemental composition, the chemistry of the inconel that we have used. As I said, the powder is inconel, the substrate is SS3161. This is the temperature dependent material properties. We choose this because we are more targeted towards the aerospace application. So inconel 625 uses in gas turbine rotors and flame. So, but you can, in simulation, it doesn't matter. For experimental validation, since we are going to do an experiment, you have to choose a material, you have to choose a substrate. But for simulation, you can do it for any material. But when it comes to validation, you have to pick and choose a material to do validation. So we did some validation studies with the powder bed fusion mission, which is built indigenously in India in RRCAT. We have utilized because it has got a lot of sensors to basically collect data, temperature data. So we utilize this particular machine there because it has got an infrared camera to capture the temperatures and also do some studies on the powder build. So this is the bed SS316L. First, we started with the single track experiments to characterize typically the prediction models of temperature. So these are the different process parameters. We selected some kind of a DOE initially to minimize our number of simulation and experimental trials. So these are some thermal simulations with the element size of 35, solid 70 models. This is the typical temperature simulation that you obtain for different process parameters, which is going to be as an input for your surrogate model. So this is the GPR model predicted temperature simulation, where we have used the sample data like number of node, X, Y, Z, and then position, and then the temperature. So this is what is given as an input. And then for the GPR actually learned from the model, from the data set that has been generated from the simulations. And it is able to predict. So we validated the GPR predicted and FEM predicted models, and we could see the laser power versus scan speed. You can just see that at higher scan speeds, at lower power, you can see that the temperature is lower, but for lower speeds, always there is going to be heat buildup. For higher laser power, there is also going to be heat buildup. So it's very natural, nothing new. This is more obvious results. For example, the temperatures are up to 1600 to 1700 temperatures, 1680, which is again the melting point of internal 625. You can see it's a close correlation of the results between FE and GPR predicted over varied range of energy densities. Energy density is calculated by the P by V into H. So this is the peak temperature that is being obtained. So here you can see that if you use a GPR surrogate-based model prediction, we are able to reduce the computational time from 14,400 seconds to 22 seconds. So you can see the complete drastic reduction by just simply doing one-time simulation and using that repeatedly for any model. So the surrogate models are able to basically simulate the entire temperature in a very short span of time. So, and we also calculated the mean average process error, and then we also did a temperature validation. Whatever temperature that we obtained, we did validation studies with the the thermal camera. So we measured the actual temperature profiles using the thermal camera, and then our simulation is getting validated. We did the calibration of the camera for for its accuracy over wider temperature range. You can see that the FE predicted and the GPR predicted and experimentally measured temperature at a close correlation. But for higher energy density, we have seen that some differences in temperature between the experimentally measured and the GPR predicted. This is largely due to higher temperature leads to larger gradients in temperature, which becomes a little difficult to model. As we observe that above 400 to 600 energy density, where the power is high or the speed is low, we could see that there is a little bit of deviations in terms of how your GPR model or either FEM model can predict the accuracy of the experimental simulation, experimental measurements. So we also could able to basically get the track dimensions to pass on in a couple thermomechanical simulations. So we could, based on the solidus and liquidus lines, you can see that it is able to basically predict the GPR predicted width and track heights can be predicted using them. So we have seen that finally that the predicted width and the predicted FE predicted and the GPR predicted and also the experimental depth are closely correlated here, and the error is much less. So you can see the line of equality, the GPR predicted width is along with the experimental width is falling in line with the line of equality, and also here for the depth, this is for the width and this is for the width, we are able to basically predict more accurately. So then we did for the distortion prediction, so where we wanted to basically select a few unit cells and then study the residual system distortion. But here, one of the important thing is like we wanted to basically define distortion as a three-dimensional deviation. And we took the maximum deviation by comparing R to part. So CAD to part comparison has been used as a means of defining distortion. So the best fit alignment, under the best fit alignment, whatever is the maximum deviation, we consider this as a value of the distortion. We define that way. And then we did a same mission, same experimental plan, but we did a cubical specimens, right? So, but using a alternate XY scanning strategy. So which has been used because this is known to basically cut down the residual sources much better than the only parallel text or only parallel to it. So this is considered to be the best in terms of arresting the residual sources. So we did use this particular kind of a scan pattern and then did few experiments with Inconel 625, and then we, to our surprise, some of the commercial tools were not able to basically give the residual stress predictions. Like for example, we used a few commercial tools. I don't want to name them for my, simulating the residual stresses. So like FEM, we have did it with ANSYS, but for microstructure, for distortion simulations, we have tried with some, like I have showed few commercial solutions there. We tried with few of the commercial solutions. We found that the results are not, for example, experimentally measured residual stresses using XRD and then, simulated residual stresses along lateral and long directions. There's a huge difference. I'll show the difference in the table here. Here you can see that this is the experimental and simulated value. In some cases, for run 4, you can see there's a drastic change here. The simulated distortion, somewhere the simulation distortions are matching, but you can see that some parts which is very difficult to get the measured residuals. So as I said, 3D printing is always very difficult to basically measure the distortions and also correlate with the simulation. So we have done with several software, not just one single software. So we use several commercial tools which can give us the distortion and residual simulations, predictions. And we found that many of the softwares fails to basically give us accurate results, partly due to the fact that our measurement method is also not so accurate. So for example, when we use XRD, which is only the surface measurement after we cut the, so we have done measurements before cutting, after cutting, and also after stress relieving. So we have done that residual stress, but for we have only compared the residual stresses that we have measured before cutting, because otherwise the stresses would have been relieved. So we have seen that even the simulations before cutting could not actually yield comparable results somewhere. So we have found that there's a a drawback in using stresses values from the commercial tools. So then we have tried to basically understand it much more in depth to see why such why simulations fail to basically do. We did a UBSD for 2 samples, which is run 2 and run 6. The run 2, which has a poor intensity, and run 6, which we could not get no reflections. We found some issues with the grain orientations, because these parts had looking at the laser power signature, we could see that the energy density is much lower here. So these are the 2 parts which much lower energy density, where it is where we have found that the solidification has not happened. The grain orientation is very random, so which actually helped us to basically understand that the residual stress measurement for lower energy density becomes much difficult, in fact, to basically simulate in the software. But when you use very high resolution, very high energy densities, for example, where we get comparable results, and you can see somewhere you can get a compressive stress, sometimes you get a tensile strength, because there are positive and negative. So with all these learnings, we choose the one software which gives us a lot of confidence in terms of the comparable results with the experimental results. So we selected that data as typically as the data for training the AI, right? So we use those simulations. So here we used different types of unit cells. First, we wanted to understand the size effect. So we varied the stud diameter from 0.5 to 2.5 mm. So we tried to maintain the lattice structure size shape by maintaining 1:3 ratio, size variations. So first we studied the size variations, and then we studied the shape variations. So we tried to basically simulate the distortions for different lattice structures, just starting with the unit cells alone, and then we built at the part level. So we have then we had some few results based on it. For example, this is the size effect. As obvious to us, we have found that the maximum distortion is for a larger size of struts, because this is more obvious, because size effects are always going to increase the stresses. For smaller sizes like 0.5 is the strut diameter. So we have found that it has got the minimum distortions, but for strut sizes which are larger than 2.5 mm had a very high distortion. So this is the process parameters that we have used, and we found the Kelvin cell, which is typically having the lowest distortion because it has got higher surface area, whereas the rest of the strut diameters, for example, truncated cube has the lowest distortion, and Kelvin has the for example, which has the lowest distortion. For example, here you can see in this lowest distortion graph, you can see Kelvin always had the lowest distortion in most of them. So the Kelvin is the yellow one, so you can see that the lowest distortion among all in the lowest strut diameter. So then we designed some parts with the unit cells of the same, and then try to basically do the validation of the residual stresses that we have measured for building the part scale model. So this is the predicted distortions of the parts actually, which use the diamond, truncated cube, FCC and BCC and Kelvin cell. You can see that the maximum distortions for FCC cells are having highest distortion here, whereas the lowest distortion is for the truncated cube. So you can see which has got the maximum distortions at the lowest level for even consistently along all the unit cells. But if you see for FCC, it typically at the higher unit cells, its distortion performance, it was much lower compared to even other shapes, right? So these are important observations that we made based on the simulations that we have actually had. So then we use the ANN predictor. This is the original distortion predicted from the commercial software. And then we also use the data points and then simulated that for commercial scale. This is one of the ANN predicted distortions. This is the distortions predicted by the commercial tools using the FEM methods or coupled with the inherent strength, right? So now you can see that, so this is the line of equality, and then you can see the cross validation of the simulation versus predicted ANN distortion. So you can see that we can get a mean square error with R square value of highest value of 0.96 and 500 icons. So we left it. So we have then trained for 500 epochs. And then we did an experimental validation with the inconal material. And then we did a, to understand how the distortions happened at the interior of the parts, we did a CT scan using computed tomography to understand how they did. So you can see that this is one example of a micro CT analysis where we have done for different BCC structure, Kelvin structure, and diamond structures. You can see the distortions at different process parameters. One of the very important learning outcomes that we have, understood that when we try to basically use, struts of very high diameter, we get high distortions. When we use struts of lower diameter, we get lower distortion. But the distortions are always on the positive side, like meaning like, so some for example, in all the 3 dimensions, only one dimension is having the lower level values, like less than the nominal dimension, whereas mostly it is above the nominal dimension in most of the cases. So we then try to validate the distortion. We try to compare the simulated value to the ANN, and then we also did a part-to-part comparison by reverse engineering the cells and trying to compare the simulation results with the reverse engineered part scale maximum distortion. So we could see that truncated cube we could not experimentally successfully fabricate, but all other we could fabricate. You can see very close correlation between the simulated value and the experimental value, except for diamond cells where the experimental value was much higher compared to the simulated and the ANN predicted value. So you can see the ANN predicted value was trying to average out the experimental and simulated. So trying to basically see that since it takes the input of both the experimental data as well as the physical data, it is able to basically closely work with the work in the nominal zone of dimensions. So reduce the reduced error and reduced order models being used to basically reduced error orders, right? So you can see that this is the typical strut diameter of 2 mm with a unit cell size of 6 mm in a 20 by 20 by 12 mm cube. So relatively very small part, but for large part, even this distortion levels could be even much higher. So with this, I want to basically summarize and then take a few questions. So one of the biggest challenges that we have faced in building a robust digital twin is the data quality, because right now we don't have very good simulation tools, where the data quality is very good, and input material property is also very difficult to basically verify and correlate. So we have used some of the Bayesian inference techniques to basically do the uncertainty quantification on the input model parameters. We are currently working on to improve the input data by using the uncertainty in material properties and things like that. And faster qualification is always a challenge. And because of the time-consuming nature of the work, many people don't want to basically build such models, which is very time-consuming, and verification validation takes a lot of effort. And there is a huge variability in the process, because when you try to validate for one material, one technology, one process, but look at the currently the PBF world. It's like we have machines which are the Chinese machines which are very, very small build volumes to large size build volumes, like 1 meter by 1 meter build volumes, 800 by 800, 700 by 700. So you can see that there is a lot of variability in the technology, variability in the material, variability in the process. How far your physics-based models and data-driven models can understand that variability and bring it to the scale. So that's another challenge. And every day new materials and processes are being improved. So bringing the data set into the digital simulation, building a digital team for it is going to be another challenge. But as we understand, the first principles are independent of the material data, but the experimental data is dependent on the material data, and then combining them is going to be really a challenge. For example, You can always change the material property from the physics-based simulations, but the moment when you try to use the experimentally derived data, so then the data only pertains to certain material system that you use in the experiment. So that kind of challenges are always there when you use physics-based AI. But inverse models can be used to effectively use, or similarity analysis can be used. So see, all those different techniques can be used to basically bring parity into the results. And the mere complexity of doing everything, like integrating everything, is another big challenge for building a digital twin for additive manufacturing. But it's an ongoing research. There's a very big team. There's a lot of, even India, there have been many research teams which are currently working in many IITs and NITs and even private companies. Industries are, trying to develop their own indigenous tools in India, and they are commercially also they are available to some extent, not to the fullest extent of all the multi-physics and multi-scale models being able to go from process to structure to function to behavior, but bits and pieces they are available. But someone wants to build this complete digital twin, it will take another 5-6 years to materialize such a thing. And there has been some digital twins already available in the market which are not verified and validated, but for a very few material systems which are bundled with a few of the machines, which are only uniquely applicable for that machine. But the moment we change the machine, we change the material system, those models might prove to be, wrongs. We have to work on improving that model over the current data that you have and things like that. So these are some interesting, observations about the challenges. And with those challenges, we also have lots of opportunity to conduct research and then come up with exciting new innovations in the digital twin development and for the simulation. So with this concluding remark, I would like to basically, allow a few questions. So thanks for this opportunity. So I'll take few questions if the
Yes, Professor. I'll read out one by one, Professor.
Okay.
Actually, I have consolidated, Professor.
Yeah,
Can
please.
Yeah, Ravi, one of the participants asked, can we perform extended FEM of AM processes for composite materials using MATLAB and Python?
Okay, I think, see, the only issue is like composites can be analyzed in most of the multi-physics models. So composite can be modeled, composites can be simulated, but processing of composites is to be done, I think, through the additive processing of composite simulation. See, there are two things. One is simulating the properties of the composite materials and understanding the behavior of the composite materials, one, or simulating the entire manufacturing process of making the composites, another one. So for simulating the properties of the composites, yes, we can do simulations, but for AM based fabrication of composite materials, yes, it is possible. For example, some of the particulate composites that we can make, the graphene composites, people have successfully simulated. Even for electronics applications, some of the carbon-based composites people have simulated, and even some of the polymer systems where aluminum plus polyamide, multi-material systems, and then even some alloys. So it is possible to make a particulate composite, but fiber composites and all, I think there are few efforts in modeling them, understanding and developing digital twin, but I am not aware of any commercial tool that can ready-made give you the process simulation for composites manufacturing through AM route. But yeah, you can use Comsol or you can use ANSYS, but still they are general purpose tools. They can predict the properties of the composite, but not actually the manufacturing of composites. But there are several routes of making composites. For example, you can use material extrusion. You can use, pultrusion-based 3D printed technique where you have the extrusion plus pultrusion combined together, and you have tape binding based 3D printing machines. You have simple metal extrusion with fiber pulling and things like this. So there are many ways of achieving composite. And if you are worried about powder bed fusion, and if you are worried about liquid phase sintering, or making a composite material through like a powder metallurgy type of a route using the powder bed fusion route, yes, it is possible to simulate. So you can define them, the particle distributions and things like that in the simulation. You can always simulate it for multi-material systems within any general purpose software, and mostly you can use only the general purpose multi-physics software. Specific purpose additive tools don't accommodate composites as such, up to my knowledge. Yeah.
Okay, Professor. Next one. After the model developed, what software can be used for the simulation? Can you tell a few software names?
Okay, so see, I think there are the computational tools that are being used that are commercially available are plenty nowadays. I think I have only shown a handful of tools, but I have a chart. I think, in fact, I didn't put it in the slide. So it's like there are more than 20-25 solutions available in the commercial space. So choosing the right solution for your problem depends upon the nature of the problem that you are trying to solve. So as I suggested, somebody has a computational, somebody have a model, and then they want to prove that the design can be successfully fabricated without distortion. Yes, you can do the distortion simulations using any of the commercial tools. But the moment when it comes to very complex models, especially models involving lattice structures, or models involving let's say multi-materials, or models involving high eutectic alloys, ternary alloys, then the modeling becomes a little bit tricky, and then it becomes a little complex. So I think I think I don't want to basically endorse any one commercial tool here, but you can explore on your own.
And one more question, Rosa. You've shown some lattice structure. Yeah. Can we use any type of scanning patterns for the lattice pattern you have shown?
Okay, so I think see, your simulation software must allow you to use only certain types of, for example, one commercial solution that I showcased here allowed only 4 different types of simulation patterns. It showed zigzag, raster, and spiral, and contour pattern. So you cannot use any other path. But luckily, if you use a general purpose software, there is a software called Full Control, where you can generate your own toolpath and use that. You can import the toolpath into the FEM. And guide the thing. So like that, you can do a lot of improvisation. Like for example, you can actually have any toolpath can be given as an input. But for specific purpose software like Additive 3D and others, you have a drop down menu that where you have only 4 options to choose. There you cannot explore with different kinds of scan paths. So like a fractal scan path you can explore. So they have fixed set of scan paths. Typically raster, contour, parallel, zigzag, and spiral, not more than that.
Okay, Professor. Is there any software available for warm process to simulate?
Pardon me, can you please?
Wire arc additive manufacturing. For
Okay.
wire arc additive.
Okay, yes. So see, I think wire is like, this is typically a welding process.
Yes.
So there has been a lot of simulation tools available in the welding domain. And those companies which has been already involved in developing the welding simulation tools, they have extended that functionality to wire arc additive manufacturing. For example, SysWeld and others. So like for example, there are commercial tools which can simulate the wire-based wire plus laser, wire plus arc, both kinds of process. So I think so you can use wire arc simulations in a conventional welding simulation, but you can also use different types of wires, different types of fillers. So for example, the CMT, which is the cold metal transfer mechanism, is the most prominent method that is available for simulation. So, but the moment when you switch from that mechanism to other mechanism, you will not be able to simulate in some commercial software. They have a limitation. So you have to work with the restricted, model physics. So what is that you are currently using? Because most of the commercial WAM systems that people sell has only the CMT type of a power source, right? So based on that, only simulation tools are developed. But if you want to, you can use a general purpose software, then you can play with wide variety of options, right? So you can build your own simulations. That's the thing. I think there are commercial solutions available, but I don't want to also tell them here. I already told few names, but I don't want to take them.
Okay, Professor. No issue.
And with a simple Google search, they can get it.
Sure, Professor. Can we predict the catchment using the models?
Okay, so it's a very interesting question. In fact, one of my other students, Dr. Reginald Elvis, he did a complete thesis on catchment efficiency. So we built both the analytical model, numerical model, and machine learning model for catchment efficiency. In fact, we published that just a week ago. So if you go to my Scholar page, you can get the recent publication. The publication actually talks about catchment efficiency. We can predict catchment efficiency. In fact, we are able to do the catchment efficiency improvement up to 25% in the for a thin wall building, especially because a lot of this DED process or wire arc additive manufacturing process, mostly deposition process used for thin wall building as of now. So we are able to demonstrate our analytical, empirical, coupled physics-based models and also machine learning models. We are able to basically improve the efficiency which we can predict. So we have also did a classifier algorithm. We compared 7 classifier algorithms to classify the process parameter window into high catchment efficiency zones, low catchment efficiency zones, and medium catchment efficiency zones. We have done a tremendous amount of data, like we have generated 200 odd data in the deposition technique and then used catchment efficiency data to train the model. So, maybe I think you can just Google search it. Very recently, last week only published the catchment efficiency based prediction models. So it is publicly available. The supplementary code and supplementary data is also available, so you can use them for further exploring and building on top of whatever we have built. Yeah.
Okay. I think these are all the questions. If there are, is there any questions? If not, I'll propose the vote of thanks. Okay, Professor, thank you. On behalf of St. Joseph's Institute of Technology, I'm honored to extend our heartfelt thanks to Dr. Senthilkumaran sir for his invaluable contribution to today's event. Your insightful presentation and dedication to digital manufacturing and metal additive manufacturing have truly enlightened us. I thank you once again, Professor. And I also thank the participant for their wonderful participation. Without you, this won't be this much successful. Thank you, Professor.
Okay, so thank you very much for the opportunity. So I think I would like to thank the organizers for giving me a platform for me to basically connect. I'm glad that I'm here today, sharing the work that we have done in our lab with the rest of the academic community who are very eager to listen to me and participate in the workshop. I also wish all the participants a good learning outcome, so to enhance your knowledge and to share your experience, and to also go back and then utilize some of this knowledge into building next generation of AM products and services and software. Thank you. Thanks for the
Thank you, Professor.
patient listening. Thank you.